Okay, hello there everyone. We'll be dealing with something new today. Again, it's related to kinematics, but we'll be dealing with uniformly accelerated linear motion. We have been dealing with that. And uniformly accelerated meaning we are dealing with constant acceleration with a uniform change in speed over a given interval of time. Means the speed is changing uniformly over the time, and linear motion obviously is related to straight line motion. Okay, today we'll deal with the equations that are related to our topic, which describe the motion of a given body under uniform acceleration. So the acceleration, you have to be clear that it's uniform and it's always constant. So the equations that we'll be dealing with are popularly known as the equations of motion. But before that, we'll need to know one more mathematical operation. Just like we did the mathematical differentiation, we'll need to know about the mathematical integration. Now it's just the opposite of differentiation, it's nothing else, just the opposite of differentiation. Now in differentiation we were concerned about an instant of time, right? Instantaneous speed, instantaneous acceleration. So from time t1 to t2, if a body is starting from time t1 and it is ending at the time t2, we were considering the instant of time at any point within that range of time. We were just considering an instant, that is t, suppose like I have written over there. So any instant, it can be any instant, the dots over there over the timeline. So we can uh, obtain it at any instant, which means we divided or restricted the range of time to one point, isn't it? We were considering the entire range. The complete range is from t2 to t1. Oh, sorry, from t1 to t2. We are obtaining delta t, that is del t. So the del t is nothing but t2 minus t1, that is from the ending minus the beginning, or the, but we are restricting it to an instant, means we are squeezing it down. Okay, restricted to an instant means which almost there is no difference in time range. Okay, delta t here becomes almost tending to 0, and that is why we had taken the limiting condition, if you remember correctly, that we had limited delta t to 0. Del t tends to 0, del s by del t gives us instantaneous speed. So this del t was restricted to 0 because we squeezed it to a particular point t as per our requirement, isn't it? So now you are clear about what we did actually mathematically. You can go through it again. Just like that, we can find the instantaneous acceleration del v by del t for delta t tending to 0. So what exactly will we be doing in integration now? We know what we did in differentiation, but as I had said earlier, it's just the opposite of differentiation. Now it means we'll be considering the entire range. Instead of going for an instant case, we'll be considering an entire range, that is from the starting to the ending, starting time t1, ending time t2, and we'll be considering this complete range, that is from t1 to t2. But what we already did that for average cases, like finding average speed or average acceleration, we were taking from the starting to the end t2 minus t1. So we considered the entire range in that t2 t1 to t2. So the total change in time was del t, and we used it to find the average speed. So what's new in this? Is there anything new? So what's the use of integration now? Now what we'll do in integration is that, though we'll be considering the entire range, that is from the beginning to the end, but we'll be taking each and every instant for it. How do we do that? Now if you see this figure, I have put each and every instant. The tick marks that you see are those instants. So one by one we take each and every instant and we add them up. That is what we do in integration. It looks pretty clumsy, from the starting till the ending point we will be taking instants, and then we'll be adding all the instants. So it's a very hectic job, one may think, though it seems very clumsy and boring, but mathematically it can be explained by just a simple formula. Okay, that's the trick that we have mathematics with us. So we can just simplify it with a formula. what is that formula? Now just if we remember correctly, v is equal to, we are not writing instantaneous anymore, we understand it's instantaneous, so v is equal to ds by dt, just like dy by dx is equal to k, that is some value, suppose, let us say. So dy can be written to be equated to k times of dx, that is dx goes gets cross multiplied. So remember, dx and dy, they are very small values of x and y. Okay, so and we took delta x to 0, just like we did delta t to 0. Del t tending to 0, we got dt. So del x tending to 0, we get dx. So these are very small values tending to 0, isn't it? So we are getting the instantaneous points. Now dy is equal to k dx, we will get the entire value, that is y, by integrating dy. The sign, that the symbol that you see over there, that s like symbol before dy, that is the integration symbol. So dy, integration of dy is giving me y, which is equal to integration of k times of dx. And just like that, differentiation, just like differentiation, we've got a formula for it. If we have dy by dx to be equal to x to the power n, again n is just a number, it's a constant, then dy has to be equal to x to the power n dx. Integration of dy will give me integration of x to the power n dx. So y is equal to x to the power n plus 1 divided by n plus 1 plus c, that is any constant, it is just an arbitrary constant. Okay, so we have, this is the formula that we obtain after integrating. So we have the entire value of y, as you know, that is the symbol for integration, that is that s like symbol, elongated s. It actually started from the summation sign that you see over there, and then it was gradually modified, and we get a more delicate elongated s symbol. So the formula that you see over there has been boxed. So y dy by dx is equal to x to the power n. So integrating that, we get y is equal to x to the power n plus 1 divided by n plus 1 plus c, where c is any arbitrary constant. This is what we obtained after integration. Any arbitrary constant means its value here is unknown, though we can know its value, mathematically we'll be seeing that. So integration of dy is equal to integration of x to the power n dx. That is how we obtained it, isn't it? That is what you saw just now. Now I'll prove it to you how it is the opposite of differentiation. Just let's do it, just to know. So dy by dx, now if I start to calculate, that will be equal to d by dx of that entire bracketed term that we have for y. So d by dx of the first term plus d by dx of c is a constant, as I told you, so constant derivative of the constant goes to 0. So now this will be equal to that 1 by n plus 1 is again a number, so it goes outside, it is also a constant. So we have d by dx of x to the power n plus 1. Now the formula, if you remember, n plus 1 x to the power n plus 1 minus 1, just like nx to the power n plus n minus 1, right? Instead of n, we have n plus 1 over here in the power of x. So n plus 1 into x to the power n plus 1 minus 1. So now these n plus 1 terms that you see over there, they get cancelled out, obviously. One at the bottom and the other at the top, so they get cancelled out. And n plus 1 minus 1, the plus 1 and minus 1 also cancel out, they equate to 0. So what is left is only n. So the value that we get after this is x to the power n, which is the same value as the previous case. If you see, I'll encircle it. Yes, dy by dx is equal to x to the power n. Initially we had got that, we integrated that, we obtained another value, then again we differentiated that to get back the same value. So now you know why the arbitrary constant is not a headache, because it goes to 0. So this is how we deal with integration, isn't it? Simple formula, the boxed formula that you see over there in the square boxes, that is the formula for integration. Now so we move over to the first equation. So we have acceleration instantaneous, I'm not writing it anymore, so we know this is instantaneous acceleration, is equal to dv by dt. We can cross multiply it, dv is equal to a dt. Now remember, we are dealing with constant acceleration every time, the uniform acceleration that I had told you right from the beginning. So integrating dv, okay, is we get the integration of a dt. Now a can go outside because it is a constant, so it can stay out of it, stay out of the integration, because constants can never be differentiated, they cannot be also integrated. So now we set a limiting range from the starting till the end. Suppose any object that we are considering over here is moving with an initial speed u at time t is equal to 0, and it reached to a final speed v at time t is equal to t, right? So mark the timings, that is t is equal to 0, we had the initial speed as u, and t is equal to t, we had the final speed to be equal to v, right? So we'll be integrating over that range. So now we put this range in the integration to set our given limits or range. So speed or velocity is taken from u to v. So if you see now in the integration sign, we have u at the bottom and v at the top, and again 0 at the bottom for dt, and t, that is the final time, at the top. So it is from the initial to the final. Initial lies at the bottom, final lies at the top. So d integration of dy, integration of dx, they all give the same thing. Dy gives y, dx gives s, dv gives v, dt gives t. So integration of these things are directly the same things as well. So integration of dv gives me v, which is equal to a times of t, integration of dt is t. And now we set the limits. So from the initial u to v, and the time varies from 0 to t. Okay, this is definite integration, unlike the one we showed you in the example. So the initial values are written at the bottom and the final values are given at the top. So as you know, it's always final minus initial, isn't it? So we subtract the initial from the final, that is v minus u, that is the final velocity, final speed minus initial speed, is equal to a times of t, that is the final time, minus the initial time, that is the starting time 0. So we have a into t. So v is equal to u plus at, u goes to the other side, becomes positive. So this gives me the first equation of motion, that is v is equal to u plus at, right? So this is how we obtain the equation of motion by using integration. In some books, okay, instead of v you may have v2, and instead of u you may have v1. So the formula changes likewise. And some other books you have v instead of v for v, and instead of u you have v0. So now the formula becomes v is equal to v0 plus at. So all of them mean the same. The initial lies there and the final is the equation. So v is equal to u plus at, it lies in the same form. So let me give you an example of how this equation is used. If a body was moving initially with a speed of 10 meter per second and accelerated uniformly at 5 meter per second square, what will be its speed after 10 seconds? So now you have the initial speed u, that is 10 meter per second, the acceleration 5 meter per second square, and you have the time to be equal to 10 seconds. So what do you need to find out? You just need to find out the final speed. The speed after means the final speed, obviously, after 10 seconds. So you have the equation now, v is equal to u plus at. Instead of u you put the value 10, and instead of a and t you put the value 5 and 10. So that gives me 10 plus 50, which is equal to obviously 60. So the final speed after 10 seconds for a uniformly accelerated motion is 60 meter per second as per the question. So we'll be doing similar problems related to the topic, okay? And let me tell you that we have 3 more equations, okay, to follow in the next video, which are the equations of motion. This is the first one, 3 to follow. Till next time, thank you.